Okay, so let's start today's lecture. So in today's lecture, we're going to continue. Okay, so we're going to continue what we have been discussing in the last lecture on the shift table of Laplace transforms. Okay, so very important thing is that last lecture we have been introducing the shift table of a Laplace transform, which means that you are able. Okay, so you are able to do either the ordinary shifts. Okay, so you're able to do either the ordinary shifts or the exponential shifts on either side of your Laplace transforms. Okay, so that means we have the following table. Okay, so let's say the shift table of Laplace transforms. Okay, so the shift table of Laplace transforms. Okay, so what does this table say? Well, the table says that if f of t is being under the Laplace transform is transformed to capital F of s, right? So then if you shift it, right? So let's say you do an ordinary shift, f t minus c multiplied by u of t minus c, right? So this is what we call it the ordinary shift, which means that you are going to move the function to the right by an amount of c. Okay, so then under the Laplace transform, you're going to do an exponential shift, e power minus c cs. Okay, so e power minus cs of f of capital F of s. Okay, so that's going to be the forward shift. Okay, so that's going to be the forward shift. Now you can also do it backward direction. So that means if you want to replace f by fs minus c, then under the inverse Laplace transforms, you're going to see e power of ct multiplied by f of t. This is an exponential shift in a pre-image, right? So that's an exponential shift. So what happened here? What happened here is that this minus c is going to agree with this minus c as well as this minus c here. But for this reverse direction, you're going to have minus c and plus c. So that's kind of the forward and backward shifts are going to kind of yield opposite sides. Okay, so the forward backward shifts are going to kind of yield opposite sides. So that's going to be kind of important. Okay, so that's going to be kind of important for this shift table. Okay, so now when you use this shift table, okay, so when you try to like apply this shift table, okay, so when you try to apply this shift table, you kind of want to work with either directions. So that means you can either go forward. So you see an ordinary shift, you want to Laplace transform it, you go forward direction, but you can also go backwards, right? So that means you see an exponential shift in the image, and you want to do you want to transform back by calculating an inverse Laplace transform. Then you're going to just have an ordinary shift on the pre-image. And similar story happens here, that if you have an exponential shift in a function, you want to kind of transform it, you can kind of pull the exponent out and transform it in an ordinary shift. So that kind of one must remember that this shift table consists of two lines, but can be worked out. Okay, so one can work them out through four different directions. It's a good family. Okay. Now let me also remind you that this shift table has been appearing in this table of Laplace transforms that you can find on your student resources. Especially line 11 is the forward, is the backward shift. So you shift the image, you work with the pre-image. And the line 16 is working with the forward shift that you shift the pre-image. You want to do an exponential shift on the image. Okay, so these kind of lines are going to help us a lot in doing calculations and solving differential equations. Okay, so therefore today's lecture is mainly dedicated to a few exercises. Okay, so we're going to kind of do some practice. Okay, so we're going to kind of do some practice on this shift table. Okay, so let's look at this problem. Can you find the inverse Laplace transform of this function? Okay, so can you find the inverse Laplace transform of this function? Okay, so let me Okay, so let's look at this example. Okay, so can you find the inverse Laplace transform of such a function? Okay, so let's work through this example. Okay, so let me put it here. Okay, so this is our example. Okay, so let me see. Okay, so this is an example. Okay, so let's look at this example. Okay, so can we find the inverse Laplace transform of this function? So that means you're trying to calculate the inverse Laplace transform e power minus 2s divided by s squared. We want to try do this inverse Laplace transform. So how are we going to do it? Well, you can see that because of linearity, this is nothing but 1 over s squared minus the inverse Laplace transform of e power minus 2s divided by s squared, right? So you're going to kind of have this scenario, right? So now for the first function, 1 over s squared, can we do the inverse Laplace transform? Well, in order to do the inverse Laplace transform, which column of the table you should look at? Well, one should look at the second column of the table. Is that good, family? Right? So you should look at the second column of the table because the first column are the image, pre-images, and the second column are the images. Now you want to do inverse transformation, so that means it's like what happened here. You should start from capital F of S. Is that good, family? Okay. So that means you look at the second column, and which column corresponds to the function 1 over s squared? Well, that means you have to do line 3, right? So that n is equal to 1 here. Okay, so that means so let me annotate. Okay, so that means I'm doing the following thing, right? So I'm just doing the following thing. I let n to be equal to 1. So that n factorial divided by Sn plus 1 is going to be 1 factorial divided by s to the power of 2. This is exactly the function you're looking at. Is that good, family? Okay, so you're going to have such a phenomenon. Okay, so once you have this, you are going to know what it's going to do. So that means you take n equal to 1. What's the inverse Laplace transform? N equal to 1, t to the power of n is just a t. So that you're going to have a t. But for this one, what happened here? Well, this is the inverse Laplace transform of an e power minus 2s 1 over s squared. So that means basically I'm having the following transformation. Capital F of s is 1 over s squared, right? So, and the inverse Laplace transform, right? So the inverse Laplace transform is f of t. We know it's equal to t. So t is corresponding to 1 over s squared. So what happened here is that the 1 over s squared is replaced by e power minus 2s 1 over s squared. So this is minus e power 2s f of s. So which line of the shift table you should use? You should still use this line of the shift table. It's just that what happened here is that you are going to have an exponential shift on the image side. So therefore, you should have a pre-image side. It should be something like an ordinary shift, t minus 2 multiplied by u actually t minus 2, something like this. Is a good fabric, right? So that remember the minus sign is being kept, and you're going to just have f of t minus 2 ut minus 2. So in the end, your result is t minus 2 multiplied by the indicator, the step function ut minus 2. Is that good, fabric? Okay, so this is how you do the inverse Laplace transform. So from the shift table, you have to kind of recognize that this exponential, right? So you kind of recognize that this exponential is not important, but you can kind of eliminate it by doing an exponential shift, right? So that's kind of the very important observation and very important method that one has to be able to use. Okay, so one has to be able to use. Now let me also mention, remind you that what is a ut minus 2? Okay, so ut, okay, so is the unit step function that we have defined. So that means ut minus 2 is going to be equal to 1 if t is greater or equal to 2, and it is 0 if t less than 2. Is that good, family? So therefore, this function is t minus 0 if t is less than 2. So which is nothing but t. Right, so and it is a t minus the t minus 2 multiplied by 1 if the t is greater or equal to 2 because of this. And t minus 2 multiplied by 1 is t minus 2. and t minus the t minus 2 is nothing but 2. So what you actually have is like a piecewise function. Okay, so the piecewise function is just having this function that it is equal to t if t is less than 2, and it becomes 2 afterwards. So that's kind of a very nice piecewise function for which the inverse, the Laplace transform is going to give you what happened here. Is that good? Okay, so that's going to be kind of initial example where we're going to use this shift table. Okay, so where we're going to use this shift table. So now let us look at how the shift tables are going to help you solve some of these differential equations. Okay, so that's going to be very important examples for our upcoming exams and the tests. Okay, so before that, let's practice one more exercise. Is that can you find the inverse Laplace transform of this function? So this function. So let me just copy the function. Okay, so let me just copy the function. So that means I want to find an inverse Laplace transform of this function. Is that good for everybody? Okay, so what is the inverse Laplace transform of this object? Well, here there is a very important and very general principle that I have reminded people. Okay, so reminded you many times that in this class, when you see quadratics, okay, so whenever you see a quadratic polynomial, you have usually you have two different ways to deal with it. Okay, so you have two different ways to deal with it. So one way to deal with it is to kind of decompose it, right? So you decompose it into s minus alpha multiplied by s minus beta if you want. The other way to do it is to write it as s minus square plus beta square, right? So you kind of completing square. So it depending on the scenario. Okay, so for example, here it's s squared minus 4s plus 5. So what should we do? Are we able to decompose them? Well, it really depends on whether or not you can factorize this. But you cannot. Really, indeed, you're going to say that this is a completing square because this is s minus 2 square plus 1. And that means you will not have real roots. You are not able to really decompose it. So that means you want to just write it as s minus 2 square plus 1. So that's the inverse Laplace transform you're looking for, right? So now which function, okay, so which function is on this table you're going to start? Well, there are two ways to do it. One is that you're going to directly find that line 9 and line 10 is going to work because the denominators are going to look exactly the same. You're going to take a is equal to 2 and b is equal to 1. You're going to have it, right? So if you use these two lines, what will be the result? Well, that means this is the L inverse of, okay, so that's L inverse. So basically you're taking, okay, so you're taking a to be equal to 1, right? So and b a equal to 2, b equal to 1. So that means you're going to have 1 s. So that's kind of you applied line 9 directly, all right? So that means you're going to have a is equal to 2. So the result is going to just directly give you e power of 2t multiplied by sine of t because it's a sine of bt, right? So sine of bt. So that's going to be the result. Is that good for everybody? Okay, so let me take, okay, so let me take this line and just to give you a more vivid observation, right? So of course you're not able to take the line on the exam, but this is just to show you what you're going to do on the exam is that you just look at this table. Okay, so you just look at this line of this table. Okay, so you look at this one, right? So you look at this one, you're going to see what happens, right? So that's a is equal to 2 and b is equal to 1. So that's what you want to do, right? So however, this problem has an alternative solution which can make use of the shift table. So how is this alternative solution? Well, the alternative solution is going to say that let's look at this one. Okay, so number 4 and number 5. So what's the difference between 4 and 5 as well as 9 and 10? So it's easy to see that on number 4, okay, so on number 4, if you just let, okay, so if you just let this capital F of s is equal to b over s squared plus b squared, then on number 9, it's you're just having the capital F of S minus A. And this, you can apply the shift table from line 11, right? So from line 11, you have this capital F of S minus A. So it must be e power at multiplied by f of t, where the f of t is, according to number 4, is sine bt. Is that good for everybody? Right? So you can see that even on this table, there are redundant lines, right? So some of these lines can be derived from other lines combined together. In this case, number 9 is a result of number 4 and number 11. And similarly, number 10 is number 5 and number 11. I'll leave it to you as an exercise. Is that good for everybody? Okay, so this is kind of quite important observations that you're going to see. Okay, so you're going to see on this problem. So basically, here what I'm saying that you let capital F of S to be equal to 1. So it's kind of usually a good idea to draw a picture when you want to transform these tables. So let me draw it here. Okay, so let's say capital F of S is 1 over S squared plus 1. Then you can see that correspondingly, small f of t is sinuses of t according to that line. So you're going to have this. Now what you want to do is that you work with s minus 2. Okay, so your capital F s minus 2. So that means you transform back because of the inverse Laplace transforms, right? So it's an exponential shift. So that's e power of 2t multiplied by sine t. Is that good for everybody, right? So basically, we're using this second line of this shift table. Okay, so the last line of this shift table. So that's going to be the result in 2 ways. Okay, so it's just to show you that the shift table are really powerful, and it can help you derive some of this. Some of these lines in the table are results of other lines of the table. They're just kind of a little bit redundant. Okay, but they are helpful because sometimes you will not have enough time to derive them by yourself on the exam, so that you can refer to the table directly whenever you want. Is that good for everybody? Okay, so that's going to be the results for the shift table. So now let's really we're going to look at differential equations, right? So how this shift table are going to help us solve the differential equations. Okay, so let's first look at this problem. Okay, so we're going to try to solve such a differential equation. Okay, so we're going to try to solve such a differential equation. Okay, so let's look at this problem. Okay, so this problem is saying that how do I solve this differential equation? Well, you see, in order to solve a differential equation, you must apply the Laplace transforms on both sides. So that means Laplace transform of y prime plus 4 times y is equal to the Laplace transform of t cubic e power of 2t. So on the left-hand side, once you kind of get very familiar with this situation, you can kind of do everything directly by yourself. Okay, so without looking at the table. But if you want to look at the table, you can look at the table. Okay, so what happened here is that Laplace of y double derivative is equal to what? S squared Laplace transform of y minus, okay, so minus s of y of 0, right? So minus y prime of 0, if you remember, right? So, and Laplace transform of y prime is s Laplace transform of y minus the y of 0. So that's going to be the scenario. And once you have this, you can see that because both derivatives initial conditions are 0, so you're going to just have Laplace transform of y. This is s Laplace transform of y. By linearity, you're going to have the Laplace transform of y double derivative minus 4 times Laplace transform of y derivative plus 4 times the Laplace transform of y. This is going to be s squared Laplace transform of y minus 4 times s of the Laplace transform of y plus 4 of the Laplace transform of y. So that's s squared minus 4s plus 4 of the Laplace transform of y. Is that good for everybody? Right? So that's the left-hand side. Now, what about the right-hand side? Okay, so what about the right-hand side? Well, the right-hand side is like a t cubed, right? So e to the power of 2t. So the right-hand side, okay, so that's the Laplace transform of e to the power, let me write it this way, t cubed. So how do we do this transformation? How do we do this transformation? Well, here, the nice idea is that we can apply Laplace transform, right? So we can apply a shift table. So if you want to apply a shift table, you must realize that if you let e to the power of 2t cubed, right? So I want to find the transformation. What should I do? Well, you can transform t cubed first, right? So what's the transformation of t cubed? Well, the transformation of t cubed can be found on line 3 of the table, where you set n equal to 3. So basically, what happened here is that if you let n equal to 3, right? So if you let n equal to 3, then the Laplace transform of t cubed is going to be equal to 3 factorial if s of the power, okay, so s to the power of, okay, so right, so it is going to be s to the power of s to the power of a cubic, right, plus 1. So that's going to be 3 factorial is 6, so 6s to the power of 4. Is that good, right? So s6s to the power of 4, right? So that means you're going to have, okay, so you're going to have 6s to the power of 4. Is that good, okay? So now what's happening here is that you're going to actually use, okay, so you're actually using this the last line of the shift table, but in the forward direction. You're not going to use it in the backward direction, but you're going to use in the forward direction. So this is kind of non-trivial because here I'm going to kind of multiply f of t by e to the power. Okay, so this is my f of t. So this is exactly e to the power of 2t multiplied by f of t. So that kind of tells you that sometimes you do not have to always use the shift table in its own direction. You can choose your own direction. It's either backward or forward. It actually has 2 different directions. Okay, if you do that, it means that you have an exponential shift in the pre-image. So therefore, you should have an ordinary shift on the image, right? But the f of s is actually given by this function. So this in result is s minus 2 to the power of 4. Is that good, everybody? Okay, so that's going to be the scenario. If you look at the scenario, it's going to be quite nice. It's going to tell you that you have this one, right? So this is the the Laplace transform on the left-hand side. So there's s squared minus 4s plus 4 multiplied by the Laplace transform of y is equal to the Laplace transform of this object. So that's e power of 2t, t to the power of 3. This is nothing but 6s to the power s minus 2 to the power of 4. So that means here, this one is s minus 2 to the power square of the Laplace transform of y. So what you get in the end is saying that Laplace transform of y is 6 to the power of s minus 2. Okay, so to the power of 6. Is that good, everybody? Okay, so that means you want to say that y is the inverse Laplace transform of 6s to the power of 2, s minus 2 to the power of 6. You want to have this inverse Laplace transform. Is that good, everybody? Okay, so but how do you calculate this inverse Laplace transform? Right, so how are you going to calculate this inverse Laplace transform? Well, that means you would like to set 6s to minus 2 to the power of 6, something is being transformed to it, right? So, and you are going to go to backwards by the inverse Laplace transform. But how are you going to look at it? Well, you look at the table, which one satisfies this table? Well, you can see that this line, okay, so this semester, the table is kind of easy, so you can use line 8 directly. But if you suppose you don't have line 8, then you have to go back to line 3. So what I'm saying is that you can see that I should work with this function first, 6s to the power of 6. Is that good, family? Okay, so what's the inverse Laplace transform of this object? Well, if you have this object, then you can see that from line 3, right? So from line 3, you're going to have n equal to 5. Is that good, family? Okay, so that basically says that I'm going to let n to be equal to 5, and then this f, okay, so 6 over s to the power of 6 can be written as 6 multiplied by, okay, so multiplied by, so let me say s to the power of 5 plus 1 over 5 factorial divided by 5 factorial. So that's what I'm going to have. Is that good, family? Okay, so this means this 5 factorial is 5, 4, 3, 2, 1, right? So it's 20. So that's kind of a 6 over 5 multiplied by 4, 3 and 2. 3 and 2 is cancelled with this one, right? So, and 5 factorial over s to the power of 5 plus 1. So this is actually 1 over 20 of 5 factorial of s to the power of 5 plus 1. Is a good family. Okay, so by the linearity of the inverse Laplace transforms, the inverse Laplace transform is given by 1 over 20 t to the power of 5. Is a good family. Okay, so you're going to have such a nice picture. 1 over 20 t to the power of 5. Is a good family. Okay, so that means this one is actually 1 over 20 t to the power of 5. Of course, you can do all these calculations on your exam paper. Okay, so you can just show to the grader that you understand how to do it. But then you can see that if this is f of s, this is nothing but fs minus 2. So you want to shift, right? So when you shift, you're actually doing an ordinary shift on the image side. So you're actually still using this line. You just have an ordinary shift on the image side, which should result in an exponential shift in a pre-image side. So that means this is going to be 1 over 20 t to the power of 5, right? So multiplied by e power of 2t. Remember, this exponential shift is going to have an opposite sign with this one. So that's kind of going to be the result, is that the solution y is the inverse Laplace transform of 6s minus 2 to the power of 6, which is 1 over 20 e to the power of 2t multiplied by t to the power of 5. Is that good, family? Okay, so that's kind of a pretty non-trivial way. Okay, so to kind of solve. Okay, so to kind of solve a differential equation using, so how many times we use the Laplace, the shift table of Laplace transform? We have been consecutively using the shift table of the Laplace transform twice. Is that good, family? Okay, so we've been consecutively using the shift table of this Laplace transform actually twice. So that's kind of a pretty non-trivial. Okay, so that's kind of a pretty non-trivial scenario. Okay, so that's kind of pretty non-trivial scenario. Is that good, family? Okay, so let's practice a few more exercises just to show you that how this type of problems are going to help you on exams. Okay, so how this type of problems are going to help you on exams. Okay, so I have two very nice examples that after grasping them, you should be fine, completely fine, not with the upcoming exam, but with the next exam. Okay, so that's let's try to look at this problem. Okay, so can you solve this initial value problem? Okay, so this is an initial value problem. Okay, so let me take it. Okay, so I want to solve this initial value problem. Okay, so let me make it small. Okay, so I would like to solve this initial value problem with the given initial conditions. Okay, so what are these initial conditions? Initial conditions are y0 and y prime of 0. Okay, so these are going to be given. Okay, so these two values are going to be given. Okay, so that's going to be the initial values. Okay, so let's say okay, so this is going to be the problem, right? So that's going to be the problem. So you can see that this is a typical example of the theme of these lectures, where we are going to continue, we're going to discuss differential equations. Okay, so with discontinuous right-hand side, right? So with discontinuous right-hand side. The right-hand side, so basically you say that this differential equation is the same thing as y double prime plus 9 times y is equal to some f of t. Well, the f of t is a step function, right? So that's equal to 0 if t is between 0 and pi, is equal to minus 18 is larger than pi. So what should we do? Well, for this typical type of example, you can see that whenever you have a step function, as we discussed in the last lecture, a step function can always, okay, so can always be written as the combination of unit step function. So in this case, you must realize that this step function is a combination of unit step function is actually minus 18 of u pi of t. Or maybe I will write it as ut minus pi. Is a good favorite, right? So the unit step function, which has a unit step at point pi, is a good favorite, right? So that's minus 18 ut minus pi. So basically, what I'm saying is that if I let f of t to be equal to 0 minus 18, okay, so if 0 less or equal than t less than pi, and this one if t greater or equal than pi, this is nothing but 18 times u of t minus pi. This is very important, the first step. Okay, so if you cannot work out this step, you're going to lose all your points for this problem. Okay, so for this type of all these type of problems, it is important that you're able to kind of first transform your function to the required form of the unit step functions that you would like to work with. Is that good, family? Okay, so that's going to be the scenario. Okay, so that's going to be the scenario. Once you have this scenario, yeah, let me also give you a remark here. For example, if I want to let f of t to be equal to minus 18 if 0 is less or equal than t less than pi, and it's 0 if t is greater than pi, what you're going to work with? Well, you must work with the following function, that is minus 18 of 1 minus u of t minus pi. You must realize that this is this function. Basically, you flipped this ft onward, right? So the 0 is replaced by 18, 18 is replaced by 0. This means that you're going to just replace, okay, so remember, if you have ut minus pi, you're going to have pi here, you're going to have 1 here, you have 0 here. But now you're going to have a reverted function. It's going to be 1 here, and it's going to be 0 onwards. This is u pi of t, and this is 1 minus u pi of t, or ut minus pi. Is that good, family? Okay, so that's going to be kind of very important. Okay, so that's going to be kind of very important for some of our exams. Okay, so let's say when I was teaching this class many years ago, there was an exam that they didn't give you this function, but they give you this function. A lot of people got confused because they don't know how to write 1 minus ut minus pi. Is a good, family? Okay, so this is just like a small tip for your problem. So now once you write this equation in this form, it means that you can apply the Laplace transform on both sides. So y double prime plus 9 times y is equal to Laplace transform of minus 18 u of t minus pi. So that's going to be kind of shows you the power of this method, right? So it really shows you the power of this method, right? So you can really start to do the Laplace transforms, because this is nothing but the let's say let me do it in one step. So that's going to be Laplace transform y derivative plus 9 times the Laplace transform of y is minus the 18 the Laplace transform of u of t minus pi. Are going to be this situation. But Laplace transform of y second derivative is s squared Laplace transform of y minus s of the y of 0 minus the y prime of 0 plus 9 times the Laplace transform of y is minus 18. You want to Laplace transform ut minus pi. So what you should do? Well, you look at the table, right? So you want to transform ut minus pi. This is exactly 917, which we have actually been calculated in class, right? So in the last lecture. So that's actually e power minus pi s divided by s, right? So e power minus pi s divided by s. Is that good, family? Okay, so now what is y0 and y prime of 0? Y0 is 2 and y prime of 0 is 0. So that means you're not going to have y prime of 0 and you have y0 is 2. So you're going to have this is 2. Is that good, family? Okay, so what do you have in the end? In the end, you get s squared plus 9 multiplied by the Laplace transform of y is equal to minus 18 e to the power minus pi s divided by s. Okay, so plus 2 times s. Is that good, family? Okay, so if you divide, then you're going to say that the Laplace transform of y is minus 18 e to the power minus pi s divided by s multiplied by s squared plus 9 plus 2 times s over s squared plus 9. Is that good, family? Okay, so that you're going to have such a nice result. Is that good, family? Okay, so that's the Laplace transform of y. Okay, so that's the Laplace transform of y. Now, what you want to do next, okay, so is to apply inverse Laplace transform. So that means y is equal to minus the 18. So I can use the linearity. So that's the inverse Laplace transform of e power minus pi s divided by s squared plus 9, right? So and then plus the inverse Laplace transform of 2 times the inverse Laplace transform s over s squared plus 9. So that's going to be the scenario. So now let us look at this inverse Laplace transforms. Okay, so that means let me continue on next board. Okay, so let me continue on the next board. So that means that y is equal to. So when copying this formula, I will take this one to be the leading term. Okay, so that's 2 times the inverse Laplace transform of s over s squared plus 9. Okay, so that's s squared plus 9. And then I'm going to have this term. Okay, so then I'm going to have this term, which I'm going to say that it is minus 18 of the inverse Laplace transform of e to the power of minus pi s divided by s multiplied by s squared plus 9. So I'm going to have this. Okay, so then you can see that I will work with this one first. So which function? Okay, so first of all, you're looking at inverse Laplace transforms, which means that you should look at the second column instead of the first column, right? So the second column is going to be important. And which function you're going to look at? Well, the denominator has to be s squared plus something. So immediately you lock yourself to 4 and 5, where you are going to set, okay, so you're going to set b. Okay, so basically you do a scratch work here. You're going to set b equal to 3. Is that good family, right? So because in the previously, what you're going to have, okay, so what you're going to have is that this b equal to 3, you're going to have s squared plus 9. So you're going to have s over s squared plus 9, right? So that being said, okay, so that being said, what you're going to see is that this is going to be, okay, so this is going to be s over s squared plus 3 squared. So therefore, you're going to use line 5. It transforms to cosine 3 of t. Is that good, family? Okay, so it transforms to cosine 3 of t. Okay, so that's going to be what you would like to have. Okay, so that means here you're going to have, okay, so this is going to be 2 times cosinuses of 3t. That's going to be a scenario. What about this one? Well, s squared plus 9 multiplied by s is immediately to find that none of these rows are going to match, right? So none of these terms. But you're not afraid of it because you have your powerful method, which is called partial fractions. So that means you would like to do a partial fraction decomposition. So that means I'm going to write it as L inverse of e power minus pi s. And then I'm going to have s over s squared plus 9. I'm going to have this. But it doesn't matter. I can do a partial fraction decomposition, right? So that's, you can see that the problems, okay, so the problems here can be very synthetic, right? So can be very synthetic in that you make use of all these methods that we have learned in this class. So basically you see that s over s squared plus 9, according to partial fraction decomposition, it should be looking like a over s plus bs plus c over s squared plus 9. So it should be something like this. And how do you determine the ABC? Well, you can determine the ABC by doing a recalculation. Okay, so that means this is a of s squared plus 9 plus b of s plus c multiplied by s. And in that case, you're going to have a plus b of the s squared plus c of s plus 9 times a. That's one is going to be divided by s squared plus 9. So that being said, it means that 9 times a is equal to 1, which means that a is equal to 1 over 9, right? So, and the c should be equal to 0, and b plus a should be equal to 0, which means that b should be equal to minus 1 over 9. So that's kind of very easy to find these formulas, that the bs plus c, this is actually a is equal to 1 over 9, b is equal to minus 1 over 9 multiplied by s, right? So that's going to be minus 1 over 9. So that's going to be a very simple partial fraction decomposition, right? So that's going to be, sorry, so here is, okay, so yeah, so I used the 1 over 9 because I pulled the 18 out. It doesn't quite matter. Okay, so that's going to be 1 over 9. Is a good family? Okay, so I will have this 1 over 9. So once you have this decomposition, you can kind of put everything, okay? So you put this formula back into here, right? So you're going to replace it. So that's going to tell us, okay? So that's going to tell us that I'm going to have y is time 2 cosinus is 3t is what I have already calculated, and then minus the 18 of the inverse Laplace transform of this object, which is the inverse Laplace transform of e power minus pi s, and then this whole thing is replaced by this. Is that good, family? Okay, so that's replaced by 1/9 of 1/s minus the 1/9 of what? 1/9 of s over s squared plus 9. You're going to have this. Is that good, family? Okay, so you do some calculations. Let's say we simplify the formula. So that's 2 cosinus is 3t minus 18/9 is 2. So that's a kind of, it's going to be 2 times the inverse Laplace transform of e power minus pi s 1/s minus the e power minus pi s s over s squared plus 9. So that's going to be the scenario. Is that good, family? Okay. But the fraction, I mean the partial, the Laplace transform is linear, so that this is nothing but 2 cosine 3t minus 2 times the inverse Laplace transform of e power minus pi s multiplied by 1/s plus 2 times the inverse Laplace transform of e power minus pi s of s over s squared plus 9. So it should be something like this. Is that good, family? Okay. So it suffices to calculate. Okay. So it suffices to calculate what is the inverse Laplace transform of this object, as well as what is the inverse Laplace transform of this object. So they are going to kind of play a very important role in our calculations, right? So now how do we do them? Well, in order to do them, we have to realize that if you let, okay, so if you let f of s, okay, so to be equal to 1/s, then you're going to have the following picture. Okay, so maybe it's better to draw this kind of pictures. So you're going to let 1/s equal to f of s. What is inverse Laplace transform? Well, it's very simple. You can just see from this table that you're going to set n equal to 0, right? So that's, I mean, it's n equal to 1, but n it can be 0. I mean, we can actually have it, right? So the inverse Laplace transform f of t is 1. So this is an example we did many times before. Now what we do is that you are going to kind of e power minus pi s f of s. What is this? This is nothing but exponential shift in an image. So the pre-image is kind of related by an ordinary shift, which means that you're going to use f of t minus pi multiplied by u of t minus pi. Remember, this minus and minus are agree with each other. If you're not familiar with this shift table, you can just look at this line 16, which kind of, you set a equal to pi, it just meets your need. Is that good for everybody? Okay, so you're going to just have this. So which means that f is 1. So this is exactly only ut minus pi. Is that good for everybody? Okay, so you don't have to really worry about this. This function is nothing. Okay, so this function, the whole thing is nothing but given by u of t minus pi. Is that good for everybody? What about this one? Well, this one is similar. So you're going to set s over s squared plus, I'm going to write it as 3 squared to be your f of s. And we have really have this in experience dealing with this function. This is nothing but line 5. Right? So where you're going to transform back to cosine 3t. So that means you're going to set the f of t is equal to cosinuses of 3t. That's going to be a scenario. Once you have this, you can see that what you want to transform is e power minus pi s of capital F of s. You want to find an inverse Laplace transform. Is that good, family? And this is nothing but an exponential shift in the image. So it should result in an ordinary shift in the pre-image. So it's ft minus pi, ut minus pi, which is nothing but cosine 3 of t minus pi. So you should replace t by t minus pi, and then multiply by ut minus pi. So that's going to be the scenario. You're going to kind of replace this function. Okay, so you're going to kind of replace this function by, okay, so you're going to replace this function by cosinuses of 3 times t minus pi multiplied by u of t minus pi. So that's going to be the scenario. Is it good, family? Okay, so this is going to be a very important type of exercise that I would like everybody to, I mean, you have the advantage that you will have the video. Okay, so please watch it. Okay, so carefully, even after this lecture, try to understand the whole procedure, right? So after the whole procedure, it means that the first step is to transform the right-hand side into unit step functions. So that's going to be very important. As long as you translated the right-hand side into unit step functions, you're able, okay, so you're able to use the unit step function and Laplace transforms to get the formula for inverse Laplace transforms, formula for y. And in order to calculate this inverse Laplace transforms, we first did the partial fraction decomposition. And after the partial fraction decomposition, we've been using these shift tables quite a lot, right? So we've been working with the exponential shifter, how do you transform it to an ordinary shifter, and finally we get a solution, right? So remember, these solutions involve step functions, so that indeed you're going to end up with a step function, which means that the step function, you end up with step function, their derivatives is going to satisfy this differential equation. So when you have the differential equation with a discontinuous right-hand side, your solution is in general a step function, right? So or piecewise function. It's not going to be kind of a smooth the sum of those turning points. Is that good, family? Okay. So that's kind of nice examples that we've been working with throughout this lecture. Okay, so throughout this lecture. Okay, so let me stop this lecture at this moment, and let's say we will come to back to this lecture in next time. Okay, so let me finish the lecture here, and I'll see you next time. Okay, so much for today.